Okay, we're live. Woo. So, yeah, let's go.
I'm so glad we got dressed.
We got there. We got there. I wasn't sure if I could click that button, but we got there. We did it. So welcome everyone to another virtual jug session. Happy October. And today we're going to be talking about Java profiling from the ground up with our friend and colleague Nitsan Wakart. Did I pronounce that correctly?
No, but nobody does. That's okay.
How should I pronounce it?
It's Nitsan Wakart, but don't worry about it.
Okay, cool.
Yeah,
imagine. So yeah, we're going to be talking about Java profiling today then with Nitsan. Nitsan works for Azul, and before we get started, let me quickly share my screen. Entire screen share. There we go. And let me just grab Keynote up. Here we go. So hopefully, can you see my screen, Nitsan?
Yeah.
You can. Awesome. So this is what's coming up, Java profiling from the ground up. I've noticed my first intentional mistake. Let's see if I can remember it.
I'm not.
How's that?
That's much better.
That's much better. Excellent. Actually, I think I probably got that wrong in a second place as well. So I'll update that now as if this is not recorded. There we go. So Java profiling from the ground up. You can follow Nitsan on Twitter at NitsanW. And Nitsan is going to give us our session today. The Virtual Jug is sponsored by Zero Turnaround, and we have a media partner of Rebel Labs. Zero Turnaround does some revolutionary developer tools, including JRebel and XRebel. Many of you know JRebel and already, and given this is a profilers talk, I'll talk a little bit about XRebel. XRebel is a new Java profiler which Zero Turnaround released last year, and it's a Java profiler which is designed to run at development, and is designed to sit in the background of your development runtime, so that as you're developing your code, you can get notifications of potential performance problems while you're writing your code. So do check that out. There's a couple of weeks free trial on that. You're welcome to go to zeroturnaround.com for more information. For those of you on virtualjug.com, you'll see both the IRC panel to the right-hand side and the live session to the left-hand side on the live session card. If you want to ask Nitsan any questions, feel free to pop them into that IRC chat, and I'll ask them live on the Hangouts. Please do share the group session. You can tweet right now if you wanted to say that you're watching Nitsan on the VJug right now, and more of your friends and colleagues will join us and we'll become a bigger group. And as ever, if you have any feedback about this session or the VJug in general, at VirtualJug or myself directly at SJMaple, feel free to tweet directly. So without further ado, let's get started then. I'll hand over to Nitsan. There we go.
Awesome.
And so let's talk about Java profiling, Nitsan. Sorry, did you want questions during as we go, or would you prefer them at the end? I can't remember.
Yeah. You shoot from the hip. If you have any questions as well, I would like the feedback rather than the quiet. So
okay.
Feel free to jump in whenever. Right. So are we on the first slide?
You are on the first slide. Assuming your first slide says Java profiling from the ground up, which I'm sure it does.
It is. Right. So that's what we'll be talking about. Java profiling from the ground up. This is the background is mostly my involvement in honest profile, but also benchmarking and profiling as part of my day job. So I like to start any talk I give with thanking everybody involved and also anybody actually attending. That's very kind of you, and if you leave halfway through, that's also okay. So thanks everyone who's involved, and thank you, Simon, for setting it all up. I work on Zing, which is a JVM made by Azul. It's only on Linux, only x86, etc. it's a wonderful JVM if you're having any GC problems, if you're running reactive applications, or that they need to be reactive and perhaps they're not as responsive as you'd like them to be. Zing is the JVM that probably solves your problems. Look it up. It's good, and I also like to comment that it's a great team developing it, and it's a pleasure to work with them. So I'm not sure we're hiring, but if we are, it's an opportunity to join us. I have a blog that some people read, including my closest friends and family, but not only. It's about performance, it's about low-level JVM stuff, and also I'm the main contributor to JC Tools, which is a lock-free data structure company, library, not a company, which is, it's sort of a library aimed at library writers, and at the moment, I think a lot of people might be using it without realizing. It's used by Netty, it's used by RxJava, so Netflix are using it, and it's also used by a few product companies that I know of, so that's been going extremely well. And without further ado, let's talk about profilers. So this is a famous quote from The Art of War, and if you're into fortune cookie sort of quotes, you probably know it. So know yourself, know your enemy. In 100 battles, you will never be defeated. It's not exactly true, but when people think about knowing what you do before you consider being able to do it, it often comes up. I like the next quote better from Sergey Kutsenko. Sergey is from the Oracle performance team and is hugely experienced and also a very nice guy to boot. And I did a talk with him in DevOps UK, and he came up with this quote, which is great. So yeah, performance is easy. All you need to know is everything. If you know the whole stack, if you know everything about the machine, the OS, the JVM, performance is really easy. Sadly, not all of us know everything, so it's somehow trickier than you'd think in many cases. I won't be covering everything, so you will not be leaving this talk knowing everything there is to know about performance. So sorry to disappoint there. Why do we profile? Why even bother? Why are we talking about profiles in the first place? The reason most people profile is because they want their application to run faster. And I've included Mr. B because someone said I looked a lot like him, but he is not me, despite rumors to the contrary.
Wow,
so yeah, we work on application. Sorry?
I thought that was you until you said it was Vin Diesel then.
It is me, but
Okay.
don't tell anyone. It's a secret. The other reason we profile, I really love this quote. It's sad when you show your fiance the flying car you've invented and you haven't got a fiance and you've glued an owl to a Renault Clio. In the context of what we're talking about, it's really sad when you think you've made something faster and it isn't, and it's actually bad, and you don't know what you're talking about. So avoid embarrassment and measure your application before you make any claims. And profile your application, you might learn some surprising stuff. I am constantly surprised by what comes up when I profile stuff. The other reason we profile is because we believe we can find the root causes to performance issues by profiling. This is from a survey that Rebel Labs did, and we can see that, database queries are in the center, in the slow database, etc. But 51.5% of our root causes are believed to be because of inefficient application code. So inefficient application code is something you can see in a profiler. That's where profilers shine. Everywhere else, the water is muddied a bit, and you'll probably need to look at more than just a CPU profiler to see what's happening. You'll need to look at OS stores. You need to, there's a myriad of tabs in different profilers to investigate different aspects of applications. But if you look at it, looking at inefficient application code, then profilers and CPU profiling is probably the right way to go. Which profiler should we use? We'll be discussing a little bit in this talk, two classes of profilers, but this is what people say they use. I qualify that because in my experience, a lot of people never open a profiler. And that's when I saw the stats on this slide, I was quite surprised, to be honest, by a few things. One is a lot of people seem to be using profilers, more so than I thought. And the other thing that sort of struck me is that a lot of people are using Java Mission Control, which is sort of a recent addition. It's a great profiler, and it's good to see people are picking it up. But still, VisualVM, JProfiler, YourKit are the big names in this space. NetBeans Profiler is the same thing as VisualVM, so you can add the two figures together. It's really dominating the market. So, Honest Profiler, which I've been involved in and we'll have a look at during this talk. Where did it come from? There was an original prototype put together by Jeremy Manson from Google. He was growing frustrated with existing profilers. He wanted something that would enable him to see further into production issues. So he wrote something together pretty rough. He put it out there as a prototype. I say pretty rough, I don't mean that as a criticism. I think, if you have something that basically works and you put it out there, great stuff can come out of it. And I think in the case of Honest Profiler, this is actually happening. So that prototype was picked up by Richard. Richard is on Twitter. He's sort of self-employed. He's giving courses and he's a great public speaker if you ever get to see him at conferences. I gave a talk about Honest Profiler with Richard in DevOps, and some of the slides in this talk are reused from there.
In fact, Richard's going to be giving a session in 10 days' time on the virtual jug as well. So he'll be our next speaker with Raul.
So definitely check him out. He's good-natured too, very forgiving, which is always good. Right, other people also chipped in, including myself, but not just myself. Of course, there's a list of committers on GitHub. One of the guys that came through with some great finds was Rajiv, and he's also on Twitter, but I neglected to put his handle now that I think of it. So look him up. Some great stuff. Okay, Honest Profiler. It's a sampling CPU profiler. We'll explain what sampling means in this context in a second. It relies on async get call trace, and we'll get to that later as well. Open source, as we discussed. It's pretty awesome, and it's pretty awesome on two fronts. One is the fact that it gets you great results, and I had some very nice feedback from Chris who codes on Twitter, saying how it helped him find a problem that other profilers fail to illuminate. So that's one great thing. But the other great thing is that it's actually very small. So if you want to understand how it works, there's not that much to dig through. And you can contribute, you can comment, you can ask, and everybody's happy to help. It is, however, a little bit ghetto. And when I say a bit ghetto, I mean, I was setting up the demo for today, and I found an issue, and I fixed it and pushed it quickly. And it's not a big commercial sort of product. It's not, that refined, but it's solid and it gives you good results, so stop complaining. Right. What is sampling? We'll have quite a few monkeys in the presentation. I forgot to mention, I am giving this presentation straight out of Cape Town, as Dr. Dre once said. And if the internet connection drops, it's because of Africa, basically. Right, sampling profilers. What's sampling? What's sampling profilers about? They sample the program on an interval, they collect data on an interval. And from those samples, we get a collection of data that we can look at to identify hotspots. We'll do a little demo in a second to sort of make it more concrete, but basically what sampling profilers often collect, it's either the currently running method, if they give you sort of a flat view, or they collect the stack to give you sort of a tree view of the methods and their relationships. So which methods call which methods, and you get a whole tree view in your profiler, which helps you identify the hot methods in the context that they happen. There's two underlying assumptions. One is that the samples are random, and I don't mean they happen randomly, but from the application's point of view, that they're arbitrary. They happen every once in a while, and they don't just happen when something special happens. And the other thing is that we assume that the sample distribution will approximate something like the time spent in the application distribution. So if we look at the samples, they'll tend to collect where we spend a lot of time, which is why I was saying the inefficient code is a good match for sampling profilers, because you'll be spending time in that inefficient code. Whereas calls into the database, you'll be spending a lot of time in the database. Your application might be busy doing lots of other things. And then, maybe the database calls will not show up as a CPU bottleneck. They will show up as a latency issue. The other thing that means is that latency issues are hard to diagnose with sampling profilers, because if you have a problem that happens on the sort of 99.999 percentile, so it only happens once every 10,000 samples, roughly, then that means it's not going to show up as a hot bit of code. Sampling profiles are good for identifying the sort of common cases, not for identifying the rare cases. So this is the simplest sampling profiler I can come up with. It's not actually a profiler, but I have seen people suggest you profiling your application like that on Stack Overflow, which is the source of all wisdom, as we know. It is simple enough to, dictate to someone over the phone in the middle of the night if you're supporting an application. And for those of you who don't know what JStack is, JStack comes out of the box with the JDK distributions, and you can run JStack to see what is the stack of all the threads in your Java applications. So we'll do just that right now. This is the infinite monkey problem image from Wikipedia. Right, there we go. So I put together a little demo for us. We'll have a look at the benchmark code just now, but right. So we'll take away this and we'll come back to it in a second. I'm using JMH. If you don't know what JMH is, I'm not using it, you should definitely look it up. It's a micro benchmarking harness that is very, very handy in running benchmarks and setting them up such that they're on toes. And from this one, I put the script I just described in a bash script, and I'm going to find the process I want to see with JPS, which lists all the processes, and then I'm going to just drop the full main, and we'll take 3 samples and look at them with this. Right. So this is what a stack looked like if you ever called, accepted print stack trace. You'll know and love these stack traces. And if you collect all of them, you can build a picture of what's happening in your application. So if you have a process that's sort of a runaway process, you want to know what it's doing, it's not logging anything, you can use JStack to find out. So there's a lot of different profilers that basically work this way. You sample every once in a while, and I'll stop that because my fan is kicking up. And what you end up with is those stack traces. That was the first live demo. It's very short. So now that we're also in the same mindset, you collect stack traces, like the ones you do with print stack trace, and then you take that sort of list and you construct a tree out of many such lists. And this is roughly a picture of how the sampling profiler interacts with your application. You'll notice that it samples every sort of interval. It doesn't have to be a fixed interval. It could be random. But because it's an interval, some things are bound to get missed. It's okay because we assume that if we sample for long enough, the stuff that really happens a lot will show up. So what sort of issues do we see with sampling profiles? This is important to understand because if you don't sample enough, then a sampling profiler is kind of useless. What you can do is switch to a tracing profiler. I believe XRebel is a tracing profiler. Correct me if I'm wrong.
That's correct, yeah.
Yeah, and it makes a lot of sense because if you do one interaction with a page, you're not going to click it 1,000 times until a sample, a large enough sample set builds up. You want to see exactly what happened the first time around. If alternatively, you do want a sampling profiler, you could set a shorter sampling interval, and then you'll get more samples because you're sampling more often. Or you could wait. Patience is a virtue. Moving on to the next problem. This is a problem when people talk about sampling profiles, they bring it up. It's a pretty rare problem, but it's still worth mentioning just to give people the right mindset. We see here method A is getting sampled, and because it happens to happen every time we sample, it's sort of like the profiler and the application are coordinating. Can this happen in real life? If you're sampling with very short intervals, it's very unlikely to happen. But let's say you're sampling every hour or every day, just, you're hoping to build a profile, but it's going to take a while. It's feasible that you'll miss, certain bits of code and that you'll hit some sort of periodicity. That's not a word, is it? Some sort of life cycle in your application that matches. So the solution to that, get a shorter interval, randomize your intervals. Yeah, it's, like I said, it's not very common. A common issue is that sample taking is expensive, which is why a lot of people don't actually use profilers in production. They don't want the performance overhead. Some profilers have a lower overhead, so you could switch sampling method, you could switch profiler, and then you'll be good, right? The other option is to learn to live with what you can change, which is always good. And alternatively, you could just make the interval longer. So if you're using a profiler and the overhead is too much to take, maybe you can live with sampling every 10 seconds or every minute. And then it'll be bearable again. It won't affect your throughput. You'll still get, small spikes in latency potentially when the profiler is hitting you, but for a lot of people, I think that could be quite an acceptable sort of compromise. Finally, the sample is biased or inaccurate. You could switch to something more accurate, and we'll discuss the differences between the at least two methods of sampling in a minute. Alternatively, you could just recognize that there is this bias, there is this inaccuracy. And when you look at the profile, you know that the problem is probably not where it told you, but somewhere nearby. So profilers, they don't, strictly speaking, lie. They tell you what they see, but what they see isn't, necessarily accurate. Right, so what's the problem with this method of sampling? It reports all the threads, as if you recall what we saw in the sort of stack trace. It reports all the threads, whether they're running or not. When we run a benchmark, usually there's one thread that's very hot. Everything else is sleeping. The GC wasn't really happening. There's a thread that waits for the benchmark to finish. It's sleeping as well. Everything gets reported. It uses GetStackTrace, which I'll explain in quite a lot of detail in a second, but that means it has a high overhead. Again, I'll get to the root cause of the overhead. It's Safepoint biased, which we'll explain, and surprisingly, it's exactly like JVisualVM, JConsole, other profilers. I believe JProfiler and YourKit have the same sort of issue. Now, that's not to say that they're useless, but it is something to consider that they have this inherent cost. So we'll be exploring that cost in a live demo shortly. So what's GetStackTrace and why does everybody use it? GetStackTrace is the official API. It's part of JVM-TI. It's part of the API that the JVM, all JVMs have to expose to tools. So someone like YourKit can develop a profile that works on Zing, it works on OpenJDK, it works on the IBM JVM or J9. It would work on all of them because to be certified as a JVM, they have to implement it. And the interface works roughly, it's a C++ interface with lots of bits and bobs, but the important bits are you give it a thread, and if it fails, it tells you it fails, but if it doesn't fail, it'll give you a list of frames. There'll be a JMethod ID, which I think we all understand roughly what that means. There'll be some sort of ID, and we'll have to look up which method it relates to. It also returns a JLocation. Now, JLocation is not related to Jennifer Lopez at all. It's, in fact, the BCI. The BCI is not a line of code. The BCI is the bytecode index. Not every BCI has a line of code because some code is generated without actually a source file, or you can compile your code such that the debug information is not in the jar. So, they don't correlate one-to-one. Even with normal Java code, they don't necessarily match in every case. So you find the closest line of code that you can to the particular BCI. If you want to look at how that's done, you can look, OpenJDK distributions come with the demo folder, and there's the hprof source code in there. And you can find that in that piece of code. Right, JavaStackTrace samples at a Safepoint. Very few people actually, I say very few people, most developers don't really know about Safepoints, so it's something worth sort of diving into. Safepoints are a JVM thread state. A JVM thread state could be at a Safepoint or not at a Safepoint. If it's waiting or idle or blocked, it's at a Safepoint already. If it's running Java code, then it's not at a Safepoint. And when I say running Java code, it is actually on CPU running, not It's not paused for GC, it's not paused for any other reason. It's either running or in the run queue. It's not at a safe point. And if you're running JNI code, then you're at a safe point. There's other sort of ways to be at a safe point, but we'll not walk into that. That's the main cases, right? And at a safe point, a thread's representation of its Java machine state is well described and can be safely manipulated. This works for GetStackTrace because GetStackTrace takes a thread and looks at it. Doesn't look at it at itself. It looks at another thread. So GetStackTrace stops that thread and then looks at the stack. And to stop it, it uses an existing mechanism. It puts it into a safe point. So it then follows that if the thread only stops at a safe point, it has to somehow stop. The way threads stop at a safe point is that they check the safe point flag, which is global in OpenJDK and thread local in Zing. So they execute what's called a safe point call. And where do we see those? We see those all the time in the interpreter. There's effectively a safe point between every 2 bytecodes on the back edge of non-counted loops, which means most for loops are counted. While loops are usually not counted unless they can be reduced to something that looks like a for loop. And we see it on method exit. We see it on method entry in Zing, but it's not really a problem. The thing is, safe points are not part of any sort of Java language specification. They're just a practicality of implementing a JVM. So all JVMs have them, but notionally they don't have to. JNI method exits have them because, like I said, when you're inside the JNI, you're already assumed at a safe point. So when you come out, you check if the safe point is happening so that you don't start running before the JVM lets you. So if we have this piece of code, and it's really irrelevant what it does, you'll notice there's a for loop, there's a while loop, and it's a method, so there's a method exit. Where will we see safe points here? If we assume all the methods we call into are actually quite small and they'll get inline, we'll only get to a safe point inside the while loop and at the end of the method. That means when we sample a JVM with GetStackTrace, we get safe point bias. So we see the red samples, and the red samples happen in time. But let's say all of these methods that get called when controller do something happens, all of them got inlined, and for whatever reason, all the loops are counted. There's no reason for the JVM to have a safe point. We'll only get a safe point at the end of do something. And up until that point, we can't sample. So we can't see any of that complexity that's inside controller do something, even though it might contribute to the main cost of that method. This is the harmless little bunny from the Holy Grail, if anyone recognizes it. So why do I say it's just a harmless little safe point? Because whenever you, it's not harmless at all, basically. When you go to Safepoint, you make everybody stop on OpenJDK. So, and most JVMs, in fact. So when when the profiler thread, that pink thread on the left, when it sets Safepoint to true, when it wants the JVM to go to a Safepoint, you can see Java J1, the first Java thread, it stops straight away. J2 keeps going and only stops, much later because it doesn't have a safe point maybe, or it was suspended and only got to run later on. And then we have J3, which is somewhere in between. We have J4, which is in JNI and just keeps running throughout. We have J5, it's in JNI and tries to resume halfway through the safe point, so it gets blocked as well. We only wanted the little itsy bit of work that's between everybody stopping and resuming everything, resuming all the threads. So the cost of stopping all the threads can become quite significant. And if you sample a lot, it means you're introducing these short or not so short pauses into your JVM lifecycle. So GetStackTrace overhead for OpenJDK, we stop all the Java threads. We collect either a single thread call trace or all the thread call traces. There's two separate sort of methods for that. And then we resume all the stop threads, regardless of collecting a single call trace or all the call traces at once. We stop everybody. So on Zing, things are slightly better. We only stop the sampled Java thread, and we collect that call trace and then resume. If you still use the stop all threads to collect all the, if you want all the stack traces at once, then you'll get effectively a global Safepoint. Right, what does that mean in real terms? So let us see. So we have this benchmark. In this benchmark, which is hashmap put is to blame, we will be seeing that hashmap put is in fact perhaps not to blame. Let's have a look at the code. This is hashmap put is to blame 1. We'll look at another variant just now. In the middle of this method, we have an array copy. Now, that array is 32K, so it's quite a large array. Copying it is going to take a while, and then we have the map remove that takes the target byte array out, and we copy into it, and then we put it back in. It's pretty silly, but it serves the purpose of showing this particular effect. So, looking at this bit of code, I don't know what sort of expectations people come with. Maybe they expect the map remove and put to be very expensive. Maybe they expect the array copy to be expensive. So let's profile it. JMH, because it is super awesome, it comes with a stack profiler in the box. So without the profiler, this is, the sort of cost we can expect from that method. It kind of sucks, right? Well, I don't know if you know that it sucks, but I can guarantee you that this is not the reason it's running so badly is because I made it run on one CPU, and the reason I did that is because if I let it use all my CPUs, you probably won't be able to hear me because my laptop is kind of miserable. Right, so let's profile it with the stack profiler, which does something very similar to what my JStack profiler did, but formats everything, and because, Triple is such a great guy, he made it all look nice and sorted everything out for me. So I'm going to use that. It's taking much longer, partly because it only has one CPU to use, and the profiler and the application are contending. So, quick reminder, we had the previous score was 5 microseconds, roughly, give or take, and this is 8 microseconds. So this is much worse. And who is to blame? Hashmap put is to blame because hashmap put is such a bad boy, right? But that doesn't really make sense because hashmap put is sort of super efficient, great guys worked on it. Maybe there's a bug in it. So, we profile this and we send a very angry email to Doug Lee and Josh Block, and they all scratch their heads and call us idiots. Why? We can prove that this is not actually the problem by tweaking the size of the array that we copy. So if I make the size of the array, say, 32 bytes, that suddenly it works much faster. The hash map is the same size. The hash map operations haven't changed, not in any meaningful way. So how come now it's faster just because the array is smaller? Why is the profiler not showing us the relevant bit of code that we want to know about? To answer that, I would have to either crack open the assembly, which I'm not going to do, or I will run a different benchmark. I can't remember the name of, so let's see which one it is. Oh yes, it's this one, which is called someone after copy is to blame. So in this one, I've added a small method that is not inline right after the array copy. And what we'll see here is that instead of hash map put, now this completely insignificant method is going to get all the blame. Now that is plain wrong because the problem is what, and it's not in my silly method, right? As we can see, someone to blame is now taking all the blame. Why is that? Let's have a look at this method. The only thing that's happening here is that now I'm calling someone to blame instead of map put after array copy. Someone to blame is a small method that calls another method that is stupidly cheap, I can guarantee you that. And I marked it as do not align. So that means the compiler is forced to not align this method. And if I ran this benchmark, if I estimated what's the cost of the stupid inline method, I'll see that it's in the nanoseconds. It's completely trivial. It can't be where the real cost is. So now we know where the real cost is, but that's not really the end of the story. Not only is this result obviously incorrect, but strange things happen with GetStackTrace, and commonly what would happen is that the number of threads that you're running will end up dominating the cost of the profiling. So if we we leave it in the default size, but we have a different parameter we can control here, which is the number of idle threads. And idle threads just sit there and they do nothing. So let's say we have, 10 of them. That seems pretty similar, right? Doesn't seem like we've made the profiling so much more expensive. How about we make it 100? All right, now we're flickering up and down. How about we make it 1,000? The cost grows with the number of threads that are idling, not with the threads that are running. So the more threads I have to send, the more I'm paying for profiling. So if you have this big application server where you have lots of thread pools and you're paying for all those thread pools that are not actually doing anything, that might be a bit painful. Right. Another thing that we need to acknowledge here is that when we're not at a safe point, so sorry, when we have lots of threads actually running, and we're doing this profiling exercise, so let's make it 20 threads running the benchmark. They only have one CPU, so they're going to contend. And I'll write out here. Okay. This is what happens. Right, this is great. Okay, so let's see what happens when we run this with print GC application stop time. This is going to write how long have we stopped in every save point that we had while running. This is running without the profiler. So you'll get some save points around startup. And even here, you can see that stopping the threads is around about the same cost as what's happening in the save points. Let's run that with the profiler and see what happens. So 20 threads. So lots of save points, because every time we get a stack trace, we need to get everybody to stop. And as you can see, the numbers flashing by. This is, the application stopped for 3 milliseconds, of which roughly 3 milliseconds we ended up waiting. So getting the stack trace is not really the problem here. The problem is waiting. Here's a 5 milliseconds, 6 milliseconds, etc. So the cost of stopping the threads dominates the cost of taking the sample. So to summarize, I will not bite this record, it is scratched. We have an alternative, right? Obviously, we're not very happy with GetStackTrace. I would, before we go on, I would just recommend people, if they're going to use GetStackTrace, and there's no reason why they shouldn't use YourKit, etc. If they're going to do that, set the sampling frequency to once a second or 10 times a second. If you do it like every 10 milliseconds, you'll start to see the effects of, pausing the application dominating what the application can do. And again, the more threads you have, the more you're paying and the more you're losing as well, because all the threads that could be running are paused. So what's async get call trace? Async get call trace is not part of JVM. It's not an official API, so not every JVM will have it. OpenJDK has it, which means the Oracle JVM has it. But as far as I know, the IBM JVM doesn't have it. Zing didn't used to have it. The reason I got involved with Honest Profile is because someone called us up and said it doesn't work. So I had to implement async get call trace for Zing. And if it doesn't work for you, then it's probably my fault. How does it work? This is a very different method than GetStackTrace. You give it the signal context, and I'll explain where that comes from in a second. And it gives you back, again, a failure code or a list of frames. Confusingly, the struct says line number, but it's not the line number, it's the bytecode index again. Why should we use async get call trace? It's built for sampling in a signal handler, so we can send the application signals. It doesn't need to be at a safe point because of that. It samples the interrupted thread. So it only samples one thread at a time. And interrupted thread, again, doesn't need to be at a safe point. I repeat myself. Why is that a good thing? Because if we had to be at a safe point, we'd have to stop all the other threads. So how do we use it? We pick a signal, You could use the bat signal. You could use sigprof, which is what most profilers use. You register a signal handler. You send the signal to the JVM. Usually you set it up as some sort of a timer. A JVM thread that is running, that is actually on CPU, will be interrupted. That is important. You're not going to see any stack traces from threads that are not running. If they're suspended, if they're waiting on a lock, if they're doing I/O, you're not going to see them in this sort of profiler. But the JVM thread that you've interrupted is now running your handler. So you call async get call trace. And this is what the workflow looks like. We have Mr. Timer to the left. It's sending a signal in. One thread gets interrupted. Everybody else gets to keep on running. It sends another signal. Another thread gets interrupted. Generally, signals don't interrupt themselves. That's default anyway. But other signals can interrupt them. And they interrupt the application at any point. So you get some limitations. You can't block. You can't allocate, because allocation sometimes involves some global lock. And if you call malloc inside malloc, everything goes very pear-shaped. And there's a whole set of limitations. There's a whole range of JVM-TI methods that you can't call while in the signal handler. So you need to work very carefully while you're working inside your signal handler code, which means you get the result from async get call trace, and you need to serialize it somehow, but you're not allowed to write to a file, for instance. So what does Honest Profiler do? We have a timer, we have the interrupt handler, and we have a lock-free queue that we write into. So it's lock-free, we're not blocking, and if it's a bounded queue, but if the queue is full, we're just going to drop the sample on the floor. There's no memset or malloc or locking, and the remaining work is done in some thread that is running in the background. That thread can do anything. It can malloc, it can do whatever it likes, because it's no longer in a signal handler. And this is a pretty picture explaining exactly what I just said. There's the OS timer thread, and eventually the processor thread will throw the data into a log file, which we will post-process to make sense out of. It's a bit tricky. One example we had, which I mentioned Rajiv beforehand, he was kind enough to point this issue out to us. GCC replaces your hand-rolled memset with a call to memset. Memset is not an option when you're in a signal handler, but GCC doesn't know what you're building for. So it sees a bit of code that looks like memset, and it just swaps it out and puts a call to the sort of OS memset for you, because obviously you don't know what you're doing, right? Thread local, the original code from lightweight Java profiler was using a thread local to keep the JNI, some of the JNI context. It works unless you get interrupted while doing a malloc, and then if that's the first time you get interrupted, you try and allocate your thread local, and everything goes wrong. So there's bits and pieces there that are quite sort of sharp and unpleasant, which is why we do most of the work in the processing thread. We look up method names for the JMethod ID and the class name and the file name and all that. We look up the line number for BCI, much like hprof does. We mean to look up the thread name, but we haven't gotten around to it, so your contribution is most welcome. And we log to the output file because, like I said, that's not really allowed. So this is a bit of an implementation detail, but it's important to understand about async get call trace, because sampling profilers that are sampling using the signal they the information they have is effectively the stack frame. So you need to somehow make your way from the stack frame to the call trace frame. You want to translate the program counter into some sort of method ID and PCI. And ignoring the frame pointer and stack pointer, which are not very important to this particular case, you want to translate from PC to PCI. The PC points to the current instruction, but not every instruction has a PCI, because something that is very simple to express in bytecode might take many instructions on your particular CPU. So again, we find the closest PCI to the program counter, and then from that bytecode index, we try and find the closest line of code. So it's a bit of an approximation game. There's a funny thing about program counters. This is a quote from mailing thread, the people discussing the perf profiler for running Linux. Again, this is a great tool that you should add to your tool belt. Andy Clean is one of the maintainers, and this is Brendan Gregg saying, I think Andy mentioned it to me, that instruction profiler was no longer reliable, and Andy's saying it never was. Why isn't it reliable? Well, first of all, in modern CPUs, there's more than one instruction happening at any one time. So the program counter can only point to one, but maybe 4 or 6 are in flight. The CPUs are allowed to sort of speculate. So maybe I have this really expensive load from memory, and I try and make progress. So the CPU is allowed to pretend the load happened and make as much progress as it, as possible until it hits some sort of dependency on that load. The instruction that will get all the blame is the dependent instruction, not the expensive instruction. There's also a bit of latency between you signaling and the CPU actually picking it up, which all adds up to the blamed instruction is often shortly after where the big cost lies. You see that with a lot of lock instructions, for instance, where you'll have this quite obviously expensive instruction, and everybody else will get the blame for it. So this is the process of translation. This is, we can't really do any better if we are going to report lines of code in Java. It's not something to cry about, but it's something to keep in mind, because again, knowing your tool, knowing that it's inaccurate and how inaccurate it can be, should help you find the right results. And this is the outcome of that. The limitations of sampling with async at call trace are that the line of code is inaccurate. You only sample the Java stack. This is part of the API. If you're in a native method, then that's not going to show up. But that's also true of get call trace. And only what is on CPU gets sampled. And that we assume is good, right? So let's do another live demo. Yay. Okay. That is probably too small to see. So I have set up my profiler, and running Honest Profiler is sort of a pain in terms of expressing yourself there. I was going to build a JMH plugin for it, but I haven't. So currently, we're just going to look at the file that it writes out. So we're going to look at hashmap put is to blame, and we profile it. One thing that's quite obvious is that the overhead isn't as bad, right? This is, around the 5 microseconds, and so was the original run. So, yay, less overhead, right? And when it terminates, we can have a look at the profile. Now, there's a bunch of scripts that come with Honest Profiler. Let's have a look. The dump script is something I just put together and I'll contribute shortly. As a GUI, which I'm not going to show, but people are very welcome to play with. It shows what you see from the console, and I'm more of a console guy anyway. So we put all the goodies into our one dash profile. We're going to have a look at them. So we, right. There we go. So we can select the format we want. Let's just get everything. Okay. I am a shocking typist, by the way. So, interestingly enough, output isn't at the top of the list, right? We get a flat profile by method, and then we scroll down past all these not really important methods. We'll get, where is it? Right. Flat profile by line. It doesn't look quite so bad if we chop it, but then we won't see exactly what we want to see. Right, so the top line we're looking at is line 82. Line 82, if we take a look here, scrolling down, line 82 is still this line. So now it's not HashMap that's getting the blame, but it's the call into it. That's quite sad, right? That's not really what we wanted. Why is that? If we pay attention, we'll notice that the percentages that Honest Profile here are quite low. Now, that is suspicious. You'd expect that to be like 90% in this case. Right? We'd expect the array copy to dominate the profile completely. What happened? To find out what happened, we're going to have a look at the log dump. And when we look at the log dump, we'll be really happy. We won't be. But at the end of the log dump, we have this count. So it says that Honest Profile processed 2,500 traces, but most of them were bad. And this is not Honest Profiler's fault, but this is just what async get call trace can tell you about when you're surprising the JVM not at the Safepoint. It says, I don't know what it is. It isn't Java, or I don't know what it is, but I'm pretty sure it is Java. I expect these samples are all in the system array copy, and they're just not getting reported. So, because that's quite a disappointing result, let's try something else. If we profile HashMap put is to blame number 2 with Honest Profiler, and while it's doing that, I'll look at what HashMap put is to blame number 2 does. In HashMap put number 2, we have an array copy that is hand-rolled. It's just, plain old Java. This is what happens. And this is something that we would expect profilers to live with a bit better, right? So this is we can see that the performance is pretty similar. This is actually quite exciting, in my opinion, that the hand-rolled version is just as intrinsic. This is all the good work that the profiler guy, the compiler guys at Oracle have been doing. Let's have a look. This is still not that great, right? Now I'm getting the 94% in HashMap put is to blame, but this is not really what I wanted to know, right? I expected to see some relevant Java code. Oh, right. that in a second. So now it says at line 100. Let's see what's at line 100. Line 100 is again the wrong line. Why is that? The reason this is happening is because there's not enough debug information just out of the box when you profile with async call trace. This is also true for Java mission control users. So if you want to get all the goodies, you need to specify something else. Right. You need to unlock the diagnostic VM options, and you need to ask for debugging non-safe points. By now we have quite an unpleasant command line to look at, but if we look at this benchmark again, we will have something a bit better. Let's do it the same number of samples. Also, we want to use the same Java that we used before. Let's have a short run because we don't care. Right. I'm not going to go into the GC application stop time not showing up when you use async call trace. You'll just have to believe me because I think we're sort of running very late at this point. Right, so if we, so we'll just filter everything else now instead of looking at the full console done. But if we look just at the profile by line, now we're seeing the hand-rolled array copy breakdown, and we see which lines are which, and this is just lovely because we're not having this issue where the wrong method or the wrong line. So the takeaway here is you need to enable the debug non-safe points information flag if you want detailed breakdowns of profiling information. This is still, we were profiling a different benchmark here. So just to demonstrate that this is still just as broken, we can do this. We don't need this flag. Safepoint doesn't make any difference to the stack profiler because it can only profile at a Safepoint. So in a few seconds, we will see what we'll see. And it will still play hash map put unless from 2 hours ago. Right. So yeah, like you see, hash map put 91%, obviously the wrong result. Okay. So takeaways from this talk. Honest Profiler has other there's the GUI view on the logs, there's the console log, also has a tree profile you can look at, but as we're running out of time, I'm going to leave it as homework to everybody listening. Right, know your profiler. If you don't know the tool that you're using, you might think that you're getting all the information that you need, but actually every profiler comes with some sort of an accuracy attached. There is no perfect profiler. I would go as far as saying, try more than one profiling method. So try Honest Profiler, try JVisualVM. I've used JVisualVM for a very long time, and I was very happy with it. The bonus with JVisualVM is that you'll see blocking code as well. So if there's blocking code where you don't expect it, with Honest Profiler, it's not going to show up, but with JVisualVM, it definitely will. Try an unbiased profiler, give Honest Profiler a go. There's also, like I mentioned, Java Mission Control, and there's Solaris Studio. Give them a go, see what you see. Maybe you'll learn something new about your application. Open source is great. you know, honest profile is an effort by a lot of people, you know, contributing bits and pieces here and there. You can be one of them. So yeah, give it a go, have a look, see if you can do something for us. That's it. Any questions came in? Simon, you still with me? You fell asleep?
Oh, yeah, we actually dropped everyone, unfortunately, in the first minute, but I've really enjoyed the session, so thank you for that. No, I'm joking. It was a great session. No questions as yet. I've just pinged the IRC chat and trying to get any in. We had one question earlier about asking if you were going to go into talking about profilers in production. I guess one of the biggest things about profiling in production is going to be your performance of the profiler itself. Are there any other gotchas in terms of using a profiler in performance in production?
That must be Google Chrome is refusing to show up. Okay. So you want to watch out for the cost of enabling the profiler. Chris asked on the meetup sort of chat, what's, you know, should you enable your profiler on regression tests? And I would say, you know, you want your regression tests to serve as a sort of an early alarm. They're not. It's not the same thing as an analysis sort of things. So if you have a regression test, I would run it without the profiler and, you know, get stable results as much as I can. And if I see a problem, I would then rerun it with the profiler. The one exception to that is if you have a very flaky regression test and you want the, you know, the profiling data for the off chance that you know, you'll catch the flaky run and you'll learn something about it. But that would be my take on the issue. One note is that Java Mission Control is licensed such that it's free for development, but there is a license cost attached to running it in production. On the one hand, you know, it might be worth it for some people. People should also consider that they might already have a license and not be aware of it. If they have some sort of you know, corporate agreement with Oracle, often that comes with a lot of stuff bundled in. So who knows? You might get lucky on that front. If you don't have a license and you want to run something that's non-biased in production, you could give Honest Profiler a go. Yeah, there's lots of different profilers out there, and yeah, we're blessed with a lot of choice. So.
Mm-hmm. And what's your opinion on when profiling should occur? I mean, obviously there's a number of different types of bugs that you can pick up in development and different types of bugs that you pick up in production. Has performance and profiling missed the trend of when testing kind of shifted left? Because it seems to be something that people do tend to leave till later on.
There's, I think there's good reason why profiling doesn't happen early. It's a shame that it doesn't happen early. Part of it is that profiling is part of an analysis phase. Sure, you can do profiling all the time, and some people with really sort of performance-focused development teams, they do profiling all the time. Most people do profiling when someone comes and complains about an issue. And the real issue is that people don't have any sort of performance regression tests in place. So they only find out about performance issues when there's real load on a production or test system. And the regression testing performance is hard. I mean, there's not as much infrastructure for it. It's trickier than unit testing, which is quite established as a practice. And also, if I run a unit test on my laptop, it might take a bit longer to run, but it'll still be correct. Whereas, running a performance test, say for Cassandra on my laptop, is completely irrelevant, right? It's
I
not
guess
the right hardware. No one would care. So I can't just run that test before I push my code in.
Yeah, this is an interesting one because this was one that this is an area which our team with XRebel had to look at really, because ours is obviously a profiler for development, and one of the things that we looked at, one of the aspects we looked at was rather than trying to look at the absolute figures. So rather than saying this method took this long on your development machine, which is wrong, we kind of took more of a relative approach, so that we said this method has actually taken over 50% of this call. But I think where we probably focus more on is things like SQL requests and stuff like that, whereby if a call is going to make 50 SQL queries in development, it's going to do something similar in your production environment, right?
My experience has been that performance testing on a developer machine it's not that it's completely useless, but it's hard to automate. So it's hard, if I gave you a regression suite of performance tests, you would get a lot of false positives or false negatives in that case. And then you'd end up not trusting it, and eventually you'll stop using it. You don't want to have that sort of relationship with a regression test. Otherwise, people just leave them to rot.
Yeah. I mean, I think with regression testing, I agree. Because it's one of those things that's entirely automated. It's a tricky one to interact with, I think. Yeah, from a profiler's point of
But
view.
if you're building one page and then you're making a small change and you try that page out, you're doing sort of manual testing. It's a lot less sensitive if I have thousands of tests and then you need to launch them when you do a build and run them and see what regressed and what hasn't. That's not really something you even want to do on your laptop, because regression tests should run for quite a bit, so you want to see them stabilize. Again, depending on what you're doing, some optimizations that can happen locally on your laptop can't happen on the sort of server machines you happen to deploy on, etc., etc. It's not, I've ran code and profiled it on my machine. I do it all the time, but I wouldn't do regression testing of performance on my machine. And when I do it manually, I have to allow for noise. And I would do it as sort of a sanity test before actually testing on a real machine. So it only saves me time as sort of an early check, not so much as a sort of full testing cycle.
Yeah, you certainly wouldn't use it by itself, like without future or performance testing or profiling further down the line as well.
Yeah. Look, it also depends on what you do. A lot of the optimizations I tend to get involved in are very, they're very focused. So I would want to run that same optimization on different, different kits, different CPUs. And then after I've done that, I would want to run them as part of larger sort of client code benchmarks and see how well that goes. It's not, it's not necessarily your typical sort of development cycle. So yeah,
Okay.
I don't know that my habits are representative of the general population.
Well, we'll see. Cool. Okay, so thank you very much, Nitsan. I'm just going to show my screen now quickly, which is just going to show you your Twitter ID again. So if you wanted to follow Nitsan on Twitter, at NitsanW for that, and Nitsan's a great guy to follow. He's very humorous on Twitter as well. So do follow Nitsan. Coming up soon, then in 10 days' time, we have generics. Past, present, and future. This is the second session that's going to be given by both Richard Warburton and Raul Gabriel Irma. So that's going to be the usual time, 5 p.m. UK time. Do check the invite, the event on Meetup for your local time zones. And let me just double check, see if we've got any other questions. Is it possible to share the slides? Yeah. Nitsan, if you send me a slide share or something like that of your slides,
I'll send you the PDF.
Perfect. We can go from there. So yeah, it just leaves me to say thank you very much, Nitsan. It's been a pleasure chatting to you, and thank you very much for your session. Everything will be posted online immediately, and you will be able to access that through the virtualjug.com. Yeah, thank you very much, Nitsan, and see everyone else soon. Cheers.
Cheers. See ya.